All right, so I want to talk about different types of reaction rates that you may hear about. So the average reaction rate is the rate at which a reaction proceeds over a time period. So we calculate the average reaction rate where we use concentrations at the beginning and end of a time period, similar to what we did in our previous example where we were looking at hydrogen peroxide decomposition. Now, with an instantaneous reaction rate, this is the rate that a reaction is proceeding at a specific time or at a specific concentration or amount of reactant. We won't look at this too much in this class, but we would calculate it, right? We would actually graph concentration versus time, and we can determine the instantaneous reaction rate by finding the slope of the straight line that's tangent to the curve at a specific time. So let's look at a graph so you can see more of what this looks like. And quickly I'll mention the initial reaction rate is the instantaneous reaction rate at time zero. So going back to our hydrogen peroxide example, here is a graph. So that same data that we saw in the last video, right, in a table format, they've graphed it. So we have time on our x-axis and we have concentration of hydrogen peroxide on the y-axis. So at each time point, every 6 hours, they calculated they looked at the amount of concentration, and this is how we end up with this graph. Now, if we wanted to determine the instantaneous reaction rate at a specific time point, it would be the tangent line to that slope of this graph here. So what they're showing here on this graph is at time point 0, this is the tangent line here that would give us the instantaneous reaction rate, which is the negative slope. So it's the negative change in concentration of hydrogen peroxide over the change in time, but it's actually at our initial time point 0. So if we just measured or calculated using graphing, right, to determine what that negative slope or negative tangent line to the slope is, we would get the instantaneous rate. They're also showing the instantaneous rate at time 12 hours, right? We got the tangent line to the slope here at this time point that would give us the instantaneous reaction rate. Now, relative reaction rates, this is the rate of reaction where we express it in terms of the change in concentration of any reactant or product. And the rate expressions of the reactants and products, they're related to each other based on the reaction stoichiometry. So here is an example. Let's say this is a template or just a made up reaction where we have little a, big A as where big A is our reactant. We form some product B and lowercase a and B represent the mole to mole ratio or the stoichiometry. So if we want to relate the rate of a reaction between the reactants and products, we take into account the reaction stoichiometry. So the rate is negative 1 over A, whatever our molar coefficient is. 1 over A, it's negative because it's our reactant, which is being consumed, over, right, our rate expression, which is the change in concentration of A over the change in time, is equal to 1 over B, which is our molar coefficient in front of our product, times the change in concentration of our product B over the change in time. So let's look at an example. We have NH3 forms into NH2 gas. And we want to write the equations that relate the rates of consumption of the reactants and the rate of formation of the products. So pause this video and write those three rates, right? Because we have one reactant that's consumed and it forms two products, and we can write our rates of reaction in relative to each reactant and each product that's formed. So once you have written it, you should have the following, right? Rate is equal to -1/2 for our reactant, our molar coefficient is 2, times the change in concentration of our reactant over the change in time, which is equal to the change in N2 concentration over the change in time, and we have a molar coefficient of 1, equals 1/3, our molar coefficient in front of our hydrogen gas, times the change in hydrogen gas concentration over the change in time. So these are the expressions that basically relate each reactant and each product, that relate the rates of reaction between the products and reactants. So we can use this because if, let's say we have a problem and we're given the rate of reaction with respect to hydrogen gas, using these expression or these relationships, we can figure out what the rate of consumption of NH3 would be, right? Or the rate of N2 formation, given that information. Okay, so I'm going to pause here and pick up with the factors that affect reaction rates in the next video.